Hi, I'm Sina Hartung from Team Ulmer, and I'll be giving the final presentation for today, which will be problem number 6, the Magnus glider. The task was glue the bottom of 2 light cups together to make a glider, which you can see right here. Wind an elastic band around the center and hold the free end that remains. While holding the glider, stretch the free end of the elastic band and then release the glider. Investigate its motion. So, my overview, I'll be talking about the phenomenon first, then I'll slightly touch on the flow field around the cylinder. We're going to talk about the relevant parameters, and then what the trajectory actually looks like of this glider. And then I'm going to compare my 2 trajectories I determined by experiment and by theory. And then I hope I investigated the motion of the glider. Well, to the phenomenon first, I got my little assistant here. Who's really good, by the way, because stretching this band isn't that easy. So I'm going to wrap the elastic band around my glider. I hope this works. Otherwise, we do Murphy's Law. All right. And that was the trajectory. So, why does the glider fly that way? This is due to a force called the Magnus force, which evidently is why the glider is called the Magnus glider. At the beginning, we have a rotating glider right here, and it's rotating that direction. And the black arrows are the relative stream of the air. Now, the Magnus force is perpendicular to that stream of the air. And at the beginning, it has a really high speed and a high rotation. Due to the Magnus force, then it goes up. As it goes up, its speed decreases, so the Magnus force decreases, as you can see by the arrows right here. At this point, the glider is standing in the air and there's no Magnus force left. So what will happen is the glider will fall down due to gravity. But as it falls down, it regains speed. So there's again the reappearance of the Magnus force right here. You can see that with the arrows. It's still rotating, and you see the arrows coming from down here. That's why the Magnus force is going that way. Well, it then goes that way because the Magnus force pulls it that way. And in the end, as you may have observed, there is a linear trajectory at the end, which is due to the main forces that are in balance, which would be the drag of the air, the gravitational force, and the Magnus force. So those 3 main forces are in balance, and that's why we have this linear trajectory at the end. That would be the phenomenon just for you as an introduction. But there's not only the forces that work on the glider, but also there's the air around the glider, right? We have to look at the medium. And there are 3 elementary solutions for a flow field. They're in every physics book. So if you take a uniform flow without an object, and you represent the object as like a dipole doublet, you add those 2 together, you get the stationary flow around the cylinder, which you can see right here. If you then add a vortex to that, you get the flow around the rotating cylinder, which looks something like this right here. So the air is not that perfect medium. Due to the viscosity of air, in reality, it looks like that. We have those little vortices right here. That's the stationary cylinder, and that's our rotating cylinder with the Magnus lift. And we did some experiment to just see the streamlines of the air, and that was our setup. We got our wind tunnel right here, which will represent the stream, or which will exert the stream, and then we got our cylinder in the middle. Well, in our stationary cylinder, we got this picture right here, and you can see how the air just flows around it, and you can kind of see the similarities to the model I just showed you. That's another picture where you can really see those streamlines around the cylinder. So now, when we try to rotate the cylinder, we get this picture right here, and you can see the streamlines. They're really close together up here, which will be important later if we try to calculate the Magnus force. And then again, there's this picture. I think you can see the streamlines again. Really nice here, and they're not that close together down here. But relevant parameters? Because there's so much going on, there must be some parameters that influence everything that's going on. And of course, there's the geometry of the glider, which would be the length and the radius and the mass of the glider. But also there's the initial velocity and some friction coefficients, and you can see the T and the R right here, which would be, for one, the friction in the translation, and the other is the friction coefficient for the rotation. Okay. So now you actually want to see what we did with the trajectories, right? Let's take a look. We determined our trajectories by experiment by just shooting the glider, which looked like this, and we spent a lot of time in the gym doing that to get the perfect trajectory, and then we video tracked all that. So that was the trajectory we got from the experiment, and then we video tracked it, and that was our graph, or the trajectory we got. And it kind of looks similar to that trajectory you saw. Well, it looks similar to the video I showed you, but it also looks similar to that one I just showed you right here. Now, what's the Magnus force doing? The Magnus force, as you can see, while the angular velocity increases and the streaming velocity increases, the Magnus force goes up. And you can see that this peak right here, those are the two, well, that's relevant for the Magnus force, right? So that's when it's really strong. That was our experimental model, and we also tried to do that by theory, because you can calculate that. And you remember how I told you about the streamlines, right? So that would be important right here. This is our little model right here. We got our cylinder, and it's rotating in this direction, and we got our flowing right here. So on top, there's a really high velocity. The streamlines were really close together. On the bottom, there's a really low velocity. And if we then look at Bernoulli's equation right here, it states that those two are equal, so that means if the velocity up is really high, then the pressure must be low, and in reverse, if the velocity on the bottom is really low, then the pressure must be really high. Then we get difference in pressure, which is that equation right down here. And if we then put those terms right here, and then we calculate that, we get this really nice equation right here. And don't get confused by this, I can explain this later, because that's actually all the relevant information that goes into the calculation of this little formula right here. But that's how we calculate the Magnus force. All right, but as I showed you, there's not only the Magnus force, there's also, well, some drags. Let's look at that. We get the total acceleration if we take what we got from the Magnus force, and all the constant is just represented as a c. That's all. That's the constant we calculated from the Magnus force. Our omega and our speed right here, and then that's the gravitational force that also we take into account. And if you then add a drag, we get the total acceleration. The drag we calculated like that. So that you can see it's the friction because it's negative, so it slows down. And in the beginning, you may have seen that it slowed, well, in the trajectory at the beginning, you may have seen that it slows down really fast. That is because the velocity goes in to the power of 2 right here. So that's why there's also a high drag at the beginning. Okay, so what we then did is we put that all into MATLAB, and we tried to simulate everything that we, well, calculated, right? And right here we got our linear equations, or our equations, and you can see that Q5 right here, which you haven't heard of yet, because there's our coefficient for the drag in the rotation, and we replaced our omega right here, which was right here. We replaced our omega with Q5, which is omega well, it's dependent on T. All right, so now you're wondering, we got that really nice trajectory, we got the experiment. Well, how does the theoretical trajectory look like, right? Because that's what we're trying to match those two. Well, let's take a look. That's the simulation of our theoretical trajectory. And you see, right here, it's the points. There's the spacing is 42 milliseconds between the points. So you can see right here, it's moving really fast, and right here there's this linear going down. All right, so that was our theoretical trajectory we got. And now we're going to compare it to our experimental trajectory. And wow, let's see, they're, well, nearly similar. They're really close, even in the beginning. And at the end, you kind of see kink right here. And they go down linear, or almost linear, right here. So that's what the trajectory looks like. And I'm just going to mention, we did it in 2 dimensions. So we didn't take into account how that might shake in the air. So we just looked at the z and dx coordinate. So what we found out while investigating the motion of the glider was that the motion is due to Magnus force. Here you can see the little picture from the beginning where I tried to explain the Magnus force. We found a comprehensive theoretical model, and well, luckily, there was a good agreement between our theoretical model and our experimental determination of the trajectory. Thank you for your attention. That was the presentation on the Magnus.
I have 2 minutes preparation for the discussion. Felix from the polymer team will be the opponent.
So hello and thank you, Sina, for a nice presentation. When I understand right what you have done, and then your main idea of a calculation is that there are different velocity fields, and so there are different
Velocity fields?
Also there's a different velocity above and under the object, and so this leads to a pressure difference, and so the pressure, it comes to a pressure exchange, and so it comes to the lifting, or to the force, to the Magnus force. Okay, my first question is about how you calculate the force. It looks, you say it always it's like a cylinder, but the coordinates where integrate. Can you go to this slide? Yes, of course. It don't look like a cylinder. What are these for
All right,
coordinates?
I'll start right here so you get a general understanding of what we did. Well, you understand that till here, right?
Yes, of course.
Okay, that's clear. Okay, so that's kind of the model of one side of our glider. And we took into account a cylindrical form. That's why we have the radius min and the radius max, and we calculated the medium and calculated and went on with that. Right here we got this area right here. You calculate that with this formula, it's just this angle right here. It's really small, but you also got the length, but it's dependent on y because you got the different.
It's similar to cylinder coordinates, but you considered that there is a lower radius in the middle.
No.
Have you considered this, or they're only a cylinder coordinates?
Look, you've got really big. The radius here is larger than the radius in the middle, right?
Yes.
And because we calculate a cylindrical force, I think that's
You
a question.
only calculated the average.
Yeah, we took the average, which we
Of course.
thought was
Okay.
a good approximation.
Do you think it's a good approximation? Because I think it couldn't be so good because when it's not a cylinder, maybe there are other. There is the velocity above. It's not equal over the surface, so maybe here it's higher or here it's lower. And do you think it's had any influence?
You mean that
to the
would it have something
force?
to do with like the surface and?
Yes, of course.
Well,
Why
we
it's
only used styrofoam as our material because it has really low density, and we thought the friction won't be that high for that material, and we didn't really use other materials. So that's one parameter we really didn't take into account that big. But of course, there'll be different effects on the trajectory if there's a different material.
Yes, of course. And the next question I have is to your measurements. Can you go to slide 24, 25, I think? Yes, of course, yeah. You have made a simulation, and why there are only discrete points, why it isn't a function, why are only points here?
Well,
it is, can't you calculate it analytic, or it is just numeric here?
yeah, well, yeah, we did that because there are approximations in our calculation.
So you can't calculate it analytic.
Well, we could have done a line because it is a model, so you could have connected those dots by line.
Okay. And here you can see there are differences. It is a systematic error, or why is this difference?
Of course, there are some coefficients that go into the theory that may be different in our experiment, like the CW coefficient, like the friction in the translation and the friction in the rotation, and that's what might cause this. But we get different. Well, that's just our theory. Is just an approximation of what like a general trajectory would look like. There are different trajectories with different geometries.
Okay.
Like, I can show you. You want to see that?
Oh, no.
Yeah. No. Okay.
It's clear.
Okay.
But I wonder why there is so
A loop?
yes, a loop there. Why it goes back?
Okay. Well,
And
you
it
can't
isn't
really
here
see
in your
right here.
experiment. Why it is in your simulation?
All right. You can't really see. We'll go back to the video because you can actually see the loop. It's really close. It's a really small loop, but this actually is a loop. I'll show you.
It is also here, but we can't see it. You say.
Well, the dots are so close together
Okay.
you can't see the point in between. But it's a really small loop right here, and we get the loop because we get a really high lift because our material. If you have like a bigger mass, for example, or a smaller length, you don't get that lift. But if you get a really high lift due to the geometry, then you may experience, or the glider may experience that loop. Well, one second, I'll show you the video again. Maybe you can
Okay.
saw stability, right?
Okay, it's
But
clear.
it's just so small that the dots are so close together.
Okay. Now my next question is to your stability of this glider. In your calculation, have you already made the assumption that your axis here is parallel to the ground, or does it?
That's what I said. We did only 2D, and we didn't take into account like the shaking and the stability. But you're right. I have to admit that's something we could improve on, because stability is definitely an aspect that influences the trajectory.
And how is the influence? What do you think when it is the Magnus force lower, or what do you think?
Well,
Is there a higher friction? Or?
I think, well, it's not mainly the Magnus force, it's other forces that like pull it that way, so it kind of shakes.
Okay, and how do you think you can improve your stabilization? Or stability, is there any option?
Well, again, we didn't really measure this, but if you look at the toilet paper roll, it flies differently. So of course you can like get really low friction to the surface,
yes.
And if you improve that, there may be like it may be.
I have one idea maybe. When you relocate the mass toward outside, then you have a higher.
How do you mean relocate the mass?
For example, you need other material. For example, iron rings on the side, and you connect it.
I don't think that'll work because that.
Theoretical. Do you think
Well,
it will improve your stabilization because then you increase your moment of inertia?
you know, if it wouldn't work practically, then I think there's really no point in talking theoretically. If it wouldn't fly, because it just wouldn't get the lift.
But when you find a material,
it would go like this, so like.
Yes, when you find a material which has the same mass, complete, and you put your mass, you relocate it outside.
So
Do you
mean
think the
it's
stability
thinner
is
here
high?
and like thicker here?
No,
And like,
you need you take an iron ring here outside, and then you connect it with a material which is really light, and so you can make a better glider. Do you think it's possible?
I don't.
Such an idea.
I think the effect would be worse. I think that wouldn't be an improvement.
Okay, why do you think so? It has the same mass and.
Trajectory. Well, do you think if you put iron rings here and you find that low, like with a material?
I think the stability is better. The stabilization is better. But
yeah, but it's really not that important for the trajectory.
okay. Then my next question is, there are holes on the sides. Have there any influence on the flight? Because I think the volume here stands nearly in this object, and so the air in you, and so when the air isn't so forced, and then there is a lower pressure, and when the air outside here is forced because of the movement, faster, and so it comes to a pressure exchange,
Sorry.
a high velocity, and so it comes to a pressure exchange, and so there can be turbulences. Do you understand what I mean?
Yeah, but not inside here. There might be
But
turbulences.
when here is a higher pressure and outside is a lower pressure, can it be that here are turbulences?
Of course, but we didn't take that into account.
But do you think, I think they have a high influence on the flight?
Well,
Because when there are turbulences, the Magnus effect could be so good.
well, the
couldn't be
Magnus
so good.
effect would still be there, but there might be a difference in direction. You know, like if it's like that, the air stream is like that, the Magnus force would be like that, and it would be like that.
But there can because of that hole there can be turbulences above, and it could destroy the Magnus force here. Don't you think so? Okay. And then came to my we came to my next question. You said that you have this C this lifting coefficient in your calculation. What is this for? Is this? What has this for a meaning?
Well, okay. I'm just going to show you something on the board. If you calculate the Magnus force, you get a lot of stuff, which would be right here. We take into account our R min and R max, which you can calculate like that. I'm not going to write it on because it will take a lot of time. And you get right here over the mass, and all that is a constant, and that's what we took into account right here. Because the two things, the lift depends on, I just those two for the Magnus force.
Thank you very much. Time for discussion is over now. And the jury members can have some questions about Martin.
Excuse me for my permanent asking, but I'm very interested in this project. Can you please switch to slide number 21? In this equation below, I think you can calculate the Magnus force. Can you explain which parameters are most important on your glider for its movement?
Omega and the velocity.
Can you explain it?
Well, that basically is the lift. Right here, that basically is the lift, which is the Magnus force that we can see. It would go up here. So the Magnus force is proportional to that part right here. So I think those are the really two relevant terms, the angular velocity and our speed. But it's also, of course, dependent on the radius. But I think those are the main components.
And length of the cylinder or the double curve?
Well, that's also important, you're right, because if you think of airplanes, they experience that lift and they're really long. Yes. Did that answer your question? Yes?
Next question.
Okay, it's a 2-for-1. Sina, could you please go to your flow field analyses where you got the turbulence? Thank you. No, that's just fine. And Felix, for you, you challenged her appearance of this Magnus effect and the presence of turbulences. With the help of this picture, could you say what influence the turbulences could have on the overall Magnus effect?
First of all, I would to say that you can't see turbulences. If there might be there, you can't see because white and white. So
right now I'm focusing on the turbulences behind the glider.
Behind?
Yeah.
Yes, I think when there is a pressure exchange, then there must get an airstream out or in, and there it wouldn't be so linear. So there were turbulences here, and I think it would destroy this Magnus effect.
Sina, could you go into more detail? You've been working with that. You assumed a laminar flow for your whole calculation.
And I think it's not a laminar flow.
Yeah, well, as I showed in this picture, of course there are turbulences behind the glider, and that does take effect right here, and it might affect the rotation of the glider, but I think what he was aiming at is this part right here, which I think, well, I couldn't tell from this picture because it's two-dimensional. Well, I couldn't say whether the turbulence is right here.
Yeah, right now I'm talking about the turbulence behind the glider.
But here?
Yeah.
Of course there would be an effect because the glider would just there would be a different rotation due to the turbulences. So that would affect our omega, which would affect our Magnus force. but I don't think they're so big. Well, we got that from our experiment that we got actually a really nice trajectory.
Well, okay. Thank you.
Other question? Yeah, from the experiment that we saw here and from your video, I had the impression that the rotational velocity omega changes with time. But I'm not sure if I have seen a graph how that changes. Did you take this into account in your
Omega
simulation?
does change because we have the coefficients in the rotation. Well, there's a drag too, so the rotation decreases over time.
The data to simulation comparison of this? Because your video tracking, I suppose,
No,
also...
our video tracking was just, no, we didn't do omega.
And in the simulation, you assume it's constant or it's part of the differential equation?
For a second, I'm really sorry for the scrolling right here. We take it into account right here, omega, independence to time, in our theoretical model.
Okay. This was the last question. And now I ask you please give your grades first for the report. Okay, we have written down. Yes, we have written down. Okay. We start from here, from left. 8, 8, 7, 8, 8, 9, 10, 8, 8, 8, 9. And now the grades for the discussion. 8, 5, 7, 8, 8, 7, 8, 6, 7, 9, and 6. We give a short feedback that we forgot it in the last stage. And we should now, I would say, what the manager gives. We have some minutes. 2 minutes. 2 minutes for feedback if someone wants to give a feedback. What
I really, yes, I
I
really liked the presentation and the way you tackled the problem, and I also was very appealed by the discussion which you led. One little problem or hint, you should try to listen to the questions to the other side and try to answer them.
Thank you. I think we had now 2 minutes feedback. And now this is the end of one feedback, 1 minute.
Very shortly, impressive, reported impressive math and physics, a lack of data.
Okay, thank you very much. And now we had 3 stages of the German Young Physicist Tournament, the second GYPT here in Dachau, and I think it was really a great event for both, and I hope it was also a great event for all you as visitors.